study what is phase velocity and group velocity. Before this, consider a particle making a simple harmonic motion like this. Now it is moving with its mean position, this mean position. So it is vibrating with some velocity, with certain velocity. This velocity is called particle velocity. So this is particle velocity. Now this wave must be traveling with some velocity. So its velocity, the velocity of a single wave, is nothing but phase velocity or wave velocity. So if you consider this wave, it will travel with some velocity. Consider this wave. So this wave is traveling with some velocity v. So this is nothing but phase velocity. We know the equation of plane wave, that is y is equal to so y is displacement, a is amplitude, we know. Sine 2 pi by lambda is wavelength, v is velocity, t is instant of time, and x is nothing but a distance from the source of disturbance. So all these quantities we know already. So this equation we can write it as omega and k, because omega is 2 pi and k is equal to 2 pi by lambda. So we know this. Omega is nothing but angular frequency. This n is a linear frequency, and this k is nothing but wave number, but we can say it is a spatial frequency. Wave number is nothing but a spatial frequency. This linear frequency is a temporal frequency, and this k, which is wave number, which is also called as spatial frequency, its definition is nothing is like waves per unit distance, and our regular frequency, which is linear frequency or temporal frequency. We always use temporal frequency. When we say frequency, we use temporal frequency, that is nothing but cycles per unit time. But wave number, spatial frequency, nothing but waves per unit distance. This is waves per unit time. This is waves per unit distance. So this is a difference between temporal frequency, which is linear frequency, and wave number or spatial frequency. So just take the ratio of omega and k. So we will get the v, velocity of this wave, because omega by k is nothing but n lambda we know as a wave velocity. So v is equal to omega by k. So we got this relation. Now as the wave is traveling with velocity v, we know its phase is constant. So omega t minus kx is constant. So if we differentiate it, we will get dx by dt as a omega by k, which is nothing but, this is all about wave velocity or phase velocity. Now consider group velocity. So group velocity is nothing but a velocity of a group of waves. That means some two or more waves are there with different frequencies or nearly equal frequencies. So they are differ in their frequencies. Now we know if we superimpose them, we will get a beat or a group of waves. We have seen the beat phenomenon in last chapter, so that is similar to this point, which is beat is nothing but group of velocity. We know this. So just remember that beat frequency, beat phenomenon. So if you add these two waves, you will get this beat like structure here. So here is maximum amplitude, minimum amplitude. So you will get beat like structures. Here is one beat, there will be another one, there will be another one. So this is nothing but group of waves. So we can show the group velocity with omega 1 minus omega 2, that is difference between the angular frequency divided by the difference between their wave number. So that will be del omega by del k, or d omega by dk. So this is nothing but a group velocity. So group velocity is a velocity of combination or superimposition of waves. So that group of waves, and here the wave velocity or phase velocity is a wave velocity of a single wave, and particle velocity is a velocity of a particle in that wave about its mean position, not the forward or the velocity in the direction of propagation, but the velocity about its mean position. And wave velocity, phase velocity or wave velocity is a velocity of that particle in the not the particle does not travel in wave, just the energy travels in this wave, we know. So it will be the velocity of wave velocity or phase velocity of a single wave in a direction of propagation. Now let's see relation between group velocity and phase velocity. So here you can see omega is vk. Differentiating this omega with respect to k, we get by product rule of differentiation. We know first term into derivative of second term plus second term into derivative of first term. So solving this, we get Vg. We know d omega by dk is nothing but Vg, that is group velocity. So v plus k dv by dk. Now, so we know also k is nothing but omega by v. So 2 pi n, that is angular frequency, linear frequency, divided by this v is equal to 2 pi by lambda, because v is nothing but n lambda. We know this relation. So just consider this. Now differentiate this equation, k is equal to 2 pi by lambda. With respect to lambda, we get 2 pi by lambda. Differentiation of 2 pi by lambda as minus 2 pi by lambda square. Now we know 2 pi by lambda is nothing but k. So just put the value here. So we got dk by d lambda is equal to minus k into 1 by L. Now consider these two terms. We just arrange the, we just separate the variables, the k by dk on this side and minus lambda by d lambda on this side. So sorry, not this lambda, d lambda. So on this side. Now we know k by dk, consider the equation 2 here k by dk. So we got the value for k by dk, which is minus lambda by d lambda. Putting this in equation 2, we get Vg is equal to v minus lambda dv by d lambda. So we got the relation. Now there are three cases. If Vg is less than v, Vg is equal to v, and Vg is greater than v. So these are three cases here. So this is a relation between phase velocity and group velocity. Here this is group velocity is equal to v, which is phase velocity or wave velocity, minus lambda into dv by d lambda. Here again v is phase velocity or wave velocity. Consider the next point, plane waves and spherical waves. So this point is very simple. You have seen spherical waves in your day-to-day life. Plane waves are not possible to see, because to have the plane waves, true plane waves, actually it is not possible in practice. But you have seen spherical waves, like if you have thrown stone into water, you have seen the waves. Consider this 2D diagram here. You have seen if you throw a stone at this distance, this position, then you will see waves are forming and they are traveling in all possible directions. So this is nothing but a spherical wave in 2D, and in 3D, if you want to see the spherical wave, if you create a disturbance at this position, this disturbance, this wave will travel, the spherical wave will travel in all possible directions in 3 dimensions. Okay, all 3 directions or all 3 dimensions. So this is in 3D. Now this intensity of this spherical wave decreases as the distance increases. So we know this relation, it is inversely proportional to the distance, or we can say the inverse square of the distance. So 1 by r square. Now if you want to observe plane waves, if you see these waves at a very large distance, then you can see a plane structure or a plane wave or plane wave front here. So this you can take it as a plane wave or plane wave front here. So plane wave front, so you can achieve it at a very large distances due to the spherical waves. So at a very large infinite distances, the spherical waves appear to be plane waves. So first of all, consider ultrasonic waves. We know what are ultrasonic waves. The waves which have the frequency about 20 kilohertz range. So the frequency range is 20 kilohertz. So these waves are called ultrasonic waves, that is beyond the audible limit of human ear. Now consider the piezoelectric effect. For this we need crystals like quartz, rochelle, salt, tourmaline, etc. So if we take a quartz crystal like this and we stretch or compress it by its two faces like this, so for due to this we will get a EMF generated along these two opposite faces. So this is called piezoelectric effect, and converse piezoelectric effect is nothing but if you apply electric force or EMF along these two faces, then we will get strain or stress, or we can say pressure variations, that is compressions and rarefactions along these two faces. So this is nothing but converse piezoelectric effect. point is how to generate ultrasonic waves. So this is a point where we will produce ultrasonic waves using piezoelectric generator. Piezoelectric generator works on a converse piezoelectric effect. That is, if we apply alternating EMF on two opposite faces of a crystal like quartz, you will get vibrations along the another two opposite faces of that crystal. So these vibrations create ultrasonic waves. Consider this formula. N is the frequency of the crystal, P is the loops, number of loops, L is the length of the crystal, Y is Young's modulus, rho is the density of that crystal. Now note that if natural frequency of that crystal, we know every crystal, every body has its natural frequency. If this natural frequency is exactly equal to, that is, it matches with the applied EMF, then the resonance occurs, that is condition of maximum energy, maximum output. Let's study the construction and working. So this is a circuit diagram of piezoelectric generator. Here we are using the coils L1, L2, L3, the the condenser C1, and so this is the input. These L1, L2 coils are connected with L2 using induction. Okay. So here you can see this is a quartz crystal. This crystal is connected with this circuit with A and B. These are the metal plates. Now when we apply the EMF from this circuit, we can give the crystal gets frequency from this circuit and it starts to vibrate. So we get ultrasonic waves as high as 5 into 10 power 8 hertz. Let's study the detection of ultrasonic waves. Consider first method, Cone's tube. We use the Cone's tube, pass a stationary ultrasonic waves into it, through it, and at the nodes we know the displacement is very small, or it is nearly stationary. So that powder in that tube, we introduce powder in that tube, so that powder in this tube gets collected at the nodes. Okay, so at the nodes, because the displacement at the nodes is nearly zero, and here at antinodes there is a displacement, so the powder gets collected at the nodes. So we know the distance between two successive nodes or antinodes is nothing but lambda by 2. Similarly, we can use quartz crystal. That is, if you incident quartz, the ultrasonic waves on a quartz crystal, it will create pressure variations in that crystal and creates alternate voltage across its opposite faces of another pair. So you can use this quartz crystal as a producer as well as a detector of ultrasonic waves. Third one is sensitive flame. Similarly, the Kunz tube, if you place the flame at these nodes, it will flicker because there are alternate compressions and rarefactions at this point. They very the pressure variations at these nodes is very high as compared to antinodes. Hence the flame flickers at these nodes. So again we can detect the ultrasonic waves, that is lambda by 2. We can get lambda by 2, that is a distance between two nodes or antinodes. So fourth one is the thermal detectors. Fine platinum wire is moved along the medium in which we are detecting the ultrasonic waves at the antinodes. Because of the at antinodes there is no change in pressure, so there are no change, or we can say adiabatic change in temperature. So there the platinum wire does not show any resistance, but it shows change in resistance at the nodes because there occurs adiabatic change as there is a change in pressure. So this adiabatic change changes its temperature, and we can sense this temperature as a change of resistance of that platinum wire. So this is the fourth one method of detection of ultrasonic waves. Let's consider the properties of ultrasonic waves. The first one is highly energetic. That means we know ultrasonic waves are high frequency waves. We know high frequency means high energy. The second one is wavelength of ultrasonic waves is very small. That is, they can spread very little. Hence they can travel very long distance without loss of energy. That is highly directional. Obviously these waves travel with speed of sound. As these are pressure variations, they cannot travel through vacuum. If ultrasonic waves are traveling through homogeneous medium, they will travel uniformly, but they are traveling in a non-homogeneous medium, then at each discontinuity or crack or impurity, their amplitude or intensity will decrease. If any body or material absorbs ultrasonic waves, it gets heated because we know they are highly energetic waves. If it penetrates human body, it sends various strengths of echoes with various densities, so we can use it in medical purposes. Now let's see the applications of ultrasonic waves. We know the property like high frequency, low loss of energy, and high directionality. So they can use that for signaling over large distances. So we all know what is sonar. Sonar is nothing but sound navigation and ranging. We use it to detect the position or depth of a object. So we send a ultrasonic wave, it gets reflected from that object, that echo we collect, and we just calculate its direction from our position, or its position and direction from our position. So we know we use it in ships, submarines, and determine the depth of the sea. So the formula is simple. D is equal to V. V is velocity of ultrasonic waves. T is time. So distance is V dot T. But we receive the we calculate the time after reflectance. So the distance traveled is twice. So we just divide with 2, and we get the direct distance or the depth of sea level. Or on to solder aluminum, it cannot be soldered by all ordinary soldering methods. So ultrasonic waves are used to oxide the films and facilitate soldering. That means it opens up the soldering faces. It removes the oxide film between the two surfaces. It also detects cracks in metals, and in medical applications we can use for bloodless surgery, sterilization, and sonography.